Now that we've found the area between a function and the x-axis and total area, now we're going to take a look at the area between two curves or two functions. Let's go take a look at example 1. We have f of x equals 12 over x and g of x equals 8 minus x. We want to find the area between these two functions. Now I decided before we get going with the steps, let's take a look at the graph. Alright, so here you can see we have f of x, which is 12 over x, which is a curved rational function, and g of x. We want to find this area between the two. I'm going to go ahead and show that area in green. Now the question is, just given the equations, how do we know that this is what we're trying to solve for, the area between the two? And how do we know where these functions cross that will give us the boundaries of this area? Well, that's what we're going to figure out, and we're also going to figure out what this area in between these two is. So let's take a look. The first thing we're going to do is set the functions equal to each other. This is going to be where those x values are that they cross. So this will give us this x value here and this x value down here. Without that, we really have no boundaries, and we certainly can't take a definite integral without the boundaries. And remember, the definite integral is going to help us find the area. So we're going to set the functions equal to each other for step 1. So I'm just going to simply take 12 over x, which is my f function, and set it equal to my g function, which is 8 minus x. Okay, for step 2, we're just going to find the x values where they intersect. So we're just going to solve for x in this equation. For this particular equation, what I can do for step 2 is I can put this over 1 and cross multiply. So top left times bottom right is just going to give me 12, and bottom left times top right is going to give me equal to 8x minus x squared. Alright, so how do I solve that from there? Well, I'm basically going to get everything on one side and set it equal to 0 and order from least to greatest to least. Negative 8x squared plus 8x is minus 12 is equal to 0. At that point, to figure out where they cross, we are going to, there's several things we can do. Looks like we could maybe use the quadratic formula or x method. Let me take a look and see what would be better. Okay, so it looks like x method will be a little bit quicker here. The 12 is going to go on top, 8 times c, 8 on bottom. Two numbers that multiply to give you the top and add to give you the bottom would be 6 and 2. So it's going to become negative x squared plus 6x plus 2x minus 12 equals 0. And we're going to pull in negative x out of the first two and end up with x minus 6. We're going to plug a 2 out of the second 2 and end up with x minus 6. Right. So finally we get negative x plus 2 for the first factor and x minus 6 for the second. And again, these are actually equal to 0. So for our x values of intersection where they cross, we're going to get x equals 2 from this one and x equals 6 for the other one. And again, just going back to the graph, normally you don't have the graph, this is just for conceptual reasons. If we do look at the graph, we can see that indeed they do cross at x equals 2 right here and x equals 6. So step 2 is to find those x values of intersection. Otherwise, we can't have a definite integral, and we certainly won't be able to solve this problem. That leads us to step 3. What step 3 will do is allow us to figure out what those limits of integration are going to be. Let's talk a little bit about what that means. When we set up our absolute value integral, we know that they cross at 2 and 6. And I want to talk too about why we use absolute value. So let's go to the graph to get some clarification on this. Okay. First of all, but before I do that, I will just go ahead and set up the integral. We know it's going to be from 2 to 6. All right, the question is, what goes inside the integral? That's what I want to take a look at. So if you look at the area under f, it looks like this. It's this big blue area right here. Makes sense, right? And that's the area between f of x and the x-axis. Let's see if I can pull it up so we can see the x-axis better. Okay, so here we have this area right here. We can already see that the area of this blue region between f and the x-axis, or 12 over x, from 2 to 6 is 13.18. Now take a look at the area between our function g, which is 8 minus x, and the x-axis at 16. So if we take this orange area and subtract the blue area, again it's going to look like this, you should get this green area right here. Now here's the thing, what if we did the reverse? What if we did the blue area and subtracted the orange area? We would get the same green area, but we would get a negative number back. That's the only difference it would be. It's like saying 8 minus 6 is 2, so 6 minus 8 is negative 2. So it really won't matter which we do first, as long as we take the absolute value of whichever we do. So again, the blue minus the orange will give us a negative number because the blue area is not as big as the orange area. Okay, it'd be 13.18 minus 16. But it's going to give you the same number as if you do orange minus blue, as long as you make your answer negative. I'll just go ahead and show you that if we do subtract the 2, we're going to get 2.82. Now again, if you did the smaller minus the bigger, you're going to get negative 2.82. So why did I say all that? Because it really won't matter whether you do f minus g or g minus f, as long as you take the absolute value of whatever. So I'm going to go ahead and put absolute value bars around my definite integral here. Okay, and just for consistency purposes, since you really don't have to figure out which one's above and which one's below, just always do f minus g. So in this case, I'm just going to do the blue, the 12 over x minus 8 minus x, and that'll take care of it. Now notice I'm putting my second function in parentheses. That's very important. And of course there's a dx somewhere down here just to be technical, although it won't really matter when we find the definite integral. But don't forget your absolute value bars, because again, you will get a negative area right here, especially the way we're doing it now. We would get a negative area if we didn't put the absolute value bars around it. So that's step 3. We're just going to set up the absolute value integral, or integrals, as you will see sometimes. If the graphs cross more than once, we would have to set up multiple integrals. For this one, it's just one. Now we can move on to step 4, which is to integrate. So that's what we're going to do now. Okay, so how do we integrate this function? Well, again, we're going from 2 to 6. Now, I didn't really talk about that before, but this is where these two graphs cross. And so these values where they intersect, which we found from this step, those will be your limits of integration when they cross twice. If they cross 3 times, then you'd have to, so let's say they crossed at 2, 3, and 6. You'd have an integral from 2 to 3 of 1 minus another, and another integral from 3 to 6. But anyways, that will be for another example. So that's where these come from right here. So now we're just going to find this definite integral. Now, there's a couple ways to go about this. Certainly we want to distribute this minus into both of those. So let's go ahead and do that. Alright, so it's going to be the definite integral from 2 to 6 of 12 over x minus 8, and then because it's minus minus x, we're going to have to make that a plus. Alright, and all of that dx. Don't forget your absolute value bars. Whatever you get, you have to take the absolute value just to make sure it's positive. Because the area between the curves really is going to be positive no matter what, assuming you're doing upper minus lower. So how do you integrate this? Well, these two are going to be easy. Whoops. The integral of, or antiderivative of negative 8 is just going to be negative 8x. And the antiderivative of x is going to be x squared over 2. But what about 12 over x? Now remember, the integral of 1 over x is natural log of x, right? So it makes sense that the antiderivative of 12 over x would be 12 ln x. It's basically the constant multiple rule, okay? So I can see how to evaluate these antiderivatives. All right, so this first one, like I said, is going to become 12 natural log of x. Second one's going to be minus 8x. Third one's going to be plus 1/2 x squared using the reverse power rule. Don't forget your limits of integration. It's going to be going from 2 to 6. Next, you want to plug in your upper and lower limits. So I'm going to plug in 6 right here on this line. Then I'm going to plug in 2 on the bottom line. I'm going to put brackets around my lower limit. That way I know to distribute my negative appropriately. So first you're going to have 12 natural log of 6 minus 48 plus 18, or half of 36. And on the bottom you're going to have minus 12 natural log of 2. It's going to become plus 16 because it's minus 8 times 2. And then finally minus 2. 1/2 of 2 squared is 1/2 of 4, which is 2. Next, you're going to group your natural logs together and then add negative 48 plus 18 plus 16 minus 2. It's going to give you negative 16. If you recall, there is a rule for subtracting logarithms. You divide what is inside. So 6 divided by 2 is 3, and I'm going to leave my 12 on the outside. I do actually want to show one more step there. Basically, what you're doing is you're pulling a 12 out. You're left with natural log of 6, natural log of 2. And again, the rule is you just divide what's on the inside to get 6 divided by 2. Combine it into one logarithm to put to get natural log of 3. There is actually, this is about as simple as you can get it. You could move the 12 and make it an exponent, but that's not really going to simplify it. So I'm just going to rewrite this answer. And again, you want to, if you're taking a test or something, you want to write it out as accurate as possible without the decimals. Let's use green because that was the color of green on our graph. So that's the area between these two curves. Now, again, because we don't know whether it's a positive or negative, we have to put absolute value bars around that. Whoops. So I'm going to put some absolute value bars around this because I'm not really sure which one is bigger, 12 natural log of 3 or 16. As we saw from the graph, 16 is actually bigger, so we would get a negative number if we did not put these absolute value bars around our final answer. So let's take a look at the graph to confirm that. It looks like our, if we go and look at our blue, this right here, based on from what we were working with, is our 12 natural log of 3. So take 12 and you multiply by natural log of 3, you get 13.18, which is smaller than the 16. So that's why when we subtract the two, we take the absolute value to get our rounded area of 2.82. So again, if you didn't want to do the absolute value bars and you wanted to figure out the top function and then the bottom, you could have done the g minus the f. In that case, your answer would have been 16 minus 12 natural log of 3, and the absolute value bars here would not have been necessary. So that's it for the area between the two curves of these two functions. If you have any other questions about this example, let me know.